Section 4, non-covalent bonds. Hydrogen bonds. Not hydrogen bombs, but hydrogen bonds. Much more peaceful things. Hydrogen bonds. We've agreed that oxygen is greedy compared to a hydrogen. And so if I have a water molecule, I have some negative charge over there, a little bit of positive charge over there. Suppose I have another water molecule over here. I have a little bit of negative charge over there, and I got a little bit of positive charge over there. Not that much, but I got some. This is like a little magnet. It's got a positive end and a negative end. This thing's here, a little bit like a magnet, positive end and a negative end. What happens when I have two magnets? They attract.
Or repel.
Or repel. And so what's going to happen is these guys are going to attract. Now, that doesn't sound very impressive, just these two little atoms, these two little molecules. But I got more of that over here. I got more of this over here. And when I have a big cup of water, all of those molecules are doing that to each other. They're all weakly interacting by those little magnets, hydrogen bonds. So in fact, what I end up with are big cages like that. The water's all coupled to each other by these weak forces. And these aren't like huge forces. These bonds, as compared to my 80 kilocalories per mole, these are 5 kilocalories per mole. Just 5 kilocalories per mole. And it turns out that nonetheless, because I have so many of them, water is highly, highly structured. Let's take a look at water structure here. There we go. Yeah, play water. This is actually what's going on in water. There's a tremendous amount of structure. They're all coupled to each other. They're moving around some, there's structure. This is so strong, bugs can walk on water. Bugs are walking on hydrogen bonds. The net that the bugs are walking on, that surface is provided by the strength of all those hydrogen bonds. No hydrogen bonds, the bugs sink. You can tell that. You put in something that disrupts the hydrogen bonds, soap, they sink. So you may not be impressed by hydrogen bonds, any one hydrogen bond, but in aggregate, hydrogen bonds are pretty cool. Let's advance this here. I think, try that there. And we'll keep going. Keep going and going. Yeah. Think of what, next time you think of water, think about water as a highly, highly structured business. All right, enough water there. Now, strength in numbers. Next, we have ionic bonds. Sometimes we have a situation where a hydrogen may come off here and move over here to create a net positive charge here and a net negative charge there. So here, this is no longer the sharing of electrons, but really the exit of an electron from the exit of a positive charge to create a negative charge in one place and a positive charge in the other place. This is an ionic bond between charged ions here, between ions. So these depend, of course, on their distances, as any of these forces depend, of these magnetic forces depend with distance. They're also, on the whole, relatively weakish. But you add them up together, and these all have effects. Hydrogen bonds have effects. Ionic bonds have effects. Another kind of bond, even weirder, van der Waals forces, van der Waals bonds. I told you that carbon-carbon, nonpolar. Carbon-hydrogen, nonpolar. Equal sharing. That's all very nonpolar. Well, I'm slightly lying. It turns out that even though there's an equal sharing on average, at any given instant, the negative charge might be a little on one side or a little on the other side. It sort of fluctuates back and forth. But if these guys are right near each other, and it so happens at this instant, this is a little more negative and this is a little more positive, just temporarily, what is that negative going to do over here to the negative charges? Push them away. It's going to repel those negative charges. And they'll go over here a little bit. And this will become a little more positive. But of course, that's only instantaneous because it's fluctuating back and forth. When it's more positive on that side, it's going to be pulling negative charges over. So both bonds are fluctuating, but they can fluctuate in concert with each other. They entrain each other. And if you have those two bonds that are fluctuating and they can manage to entrain each other, then it's as if you have little magnets temporarily going back and forth, and that works too. Now, this is even less impressive than hydrogen bonds. This gets you an absolutely ridiculously puny 1 kilocalorie per mole. Not very impressive, is it? But if I have some big molecule, like a protein, the sum of all these forces, the sum of hydrogen bonds and ionic bonds and these van der Waals interactions add up to big, big numbers. Big numbers. And in fact, biological molecules are held together, yes, by their covalent bonds. They matter a lot. But the shape they take up depends much less on their covalent bonds than all of these non-covalent interactions that are taking place. The hydrogen bonds, the ionic bonds, the van der Waals interactions that determine whether some long molecule folds up this way or folds up that way or whatever. Now, just to make you appreciate how powerful those forces are, I bring you the gecko. The gecko can climb up glass. It can climb this way. Why is the gecko not falling down? Well, people thought maybe the gecko has, glue on its pads. It does not. What holds the gecko up? Van der Waals forces. The gecko is held up by van der Waals forces. It manages to have its palm have these little flappy pads that can make so much contact that it's making lots of these ridiculously tiny van der Waals interactions with the surface, and that is enough to hold up a gecko. Do not try this yourself, because it turns out that you lack the right kind of pads and, I'm sorry to say, are too heavy to be held up. But for something the size of a gecko, it can be held up by van der Waals interactions, strength in numbers. And we have to understand that to understand biology. You're almost done, but before we go on, we've got a couple questions for you about different kinds of bonds.